Lab 12 Time and Alarm Adjustment. The goal of this lab exercise is to use parameterized reusable counter components in a structural design to create the time and alarm adjustment mechanism. The time set component adjusts the time and the alarm to its new value under the control of the signals generated by the alarm clock controller state machine. The block diagram is as shown. Show underscore A, show underscore T, increment R, increment min are all generated by the alarm clock controller. Show underscore T and show underscore A are mutually exclusive. So is increment min and increment R. Half second is generated by pulse generator component. Time underscore data is generated by the time count component. Alarm underscore data is generated by the alarm register component of the final design. Set underscore data is the output. The time adjustment happens by loading the current alarm or current time depending upon show underscore A or show underscore T values, then increment the minutes or hour digits separately depending upon increment R or increment min values. The digits are incremented on every half second pulse. Alarm underscore data, time underscore data, and set underscore data are array of array data types containing 4 elements where each element represents a 4-bit array which is used to represent a single digit of the alarm clock. Time declarations for the 2 and 4-bit digit BCD arrays can be found in the alarm types package, where the relationship between the BCD digit and display underscore 4 array of arrays is as shown in the table. The 0th element of the array of arrays represents the LS_min component. The first element represents MS_min component. Second element represents LSR component, and the third element represents the MSR component. To set the alarm and time, time underscore set uses two loadable 2-digit BCD counters. This 2-digit binary coded decimal counter is loadable and it is an enabled counter. It counts in two 4-bit segments. The maximum count value is passed into the counter via the two generics MS_max and LS_max. One of this counter is used to adjust the R component of time or alarm, and the other counter is used to adjust the minute component of the current time or alarm. The counter loads the load underscore data value when load enable is high, and it will count only when count underscore enable is high. Let us look at the code of this counter. Declare the alarm types package by using the use clause in order to enable the use of enumerated data type display underscore 2. Declare the entity BCT2 underscore count along with its port list. We declare two generics MS_max and LS_max through which we can pass the maximum BCD count. We declare a constant 9 for better readability. We declare the signals MS, which represents the most significant digit, and LS represents the least significant digit of the count. Reset is asynchronous here, and hence it is part of the sensitivity list, and also we check for the reset value before the clock edge. When reset is low, we initialize the MS and LS values to 0. On rising edge of the clock, we load the MS and LS values from load underscore data when load enable is active. Else if count enable is high, we increment the count. We must account for the rollovers while incrementing the count. If MS is less than MS max, we check for the value of LS. If LS is less than 9, we increment the value of LS. Else if MS is less than MS max and LS is equal to 9, we Reset the value of ls to 0 and increment ms. Else if ms equal to ms max, we increment ls
until it reaches ls max value.
If ls and mx reach their max values, we reset the value of ls and ms to 0. The output op underscore data of the counter component is obtained by the concatenation of ms and ls. Let us look at the functionality of the timeset component in some more detail. It contains two instantiations of bcd2 underscore count, one for hours and other for minutes. For time adjustment, we drive show underscore ti, which enables the load enable of both the counters. This loads the minute digits of time underscore data into the minute instantiation of BCD2 count and loads the hour digits of the time underscore data into hour instantiation of the BCD2 count. When adjusting the hour, show underscore t goes low and increment hour goes high, and the hour digits are incremented on every half second pulse until increment r goes low. Similarly, if show t goes low and increment min goes high, we increment the minute component of time underscore data on every half second pulse. For alarm adjustment, show underscore A is driven high to load the alarm value into the BCD2 counters by enabling the load enable of the two counters. When adjusting the alarm, show underscore A is driven low and the hour digits are incremented on every half second pulse by the hour instantiation of the BCD2 count. If increment min is driven high, then the minute component of the alarm data is incremented on every half second pulse. We know that we must increment the time in the pattern of a 24-hour clock, that is from 0000 to 2359 and then back to 0000, where the 2 minute digits count up to 59 and the 2 hour digits count up to 23. Hence, the maximum count for the hour instantiation is 23 and the maximum count for the minutes instantiation is 59. We use these values for the generics. The output op underscore data of the hour component forms the hour component of set underscore data. Similarly, the output op underscore data of the minute instantiation forms the minute component of set underscore data. Let us code this model. Create a file time underscore set.vht. The type declarations for the 2 and the 4-bit digit BCD arrays can be found in alarm types package and hence we declare this here. We declare the entity along with its port list. We declare the component BCD2 count along with the generics, which enables us to pass the maximum count value. We shall declare the internal signals. Let us name the load underscore data of the minute instantiation to mn data, the load underscore data of r instantiation to hr underscore data, the enable of minute instantiation to mn count enable, and the enable of hour instantiation to hour count enable, the output of hour instantiation to hr op, and the output of minute instantiation to mn op. We declare the hour and minute instantiation of BCD2 count. We know that the maximum count for the minutes is 59 and hence this value is passed through the generic map. Similarly, for our instantiation, we know that the maximum count should be 23 and hence we pass this value through the generics. Load BCD counters when show underscore A or show underscore T are active. Enable minute counter when half second and increment min are high. Enable hour counter when half second and increment r are high. Set the BCD counter inputs to either time underscore data or alarm underscore data depending upon the value of show underscore t. If show underscore t is high, we load the counter with time underscore data, else with alarm underscore data. Finally, concatenate BCD counter outputs to get the time set output, which is set underscore data. Let us code the test bench file. Declare the package alarm types to enable the use of the enumerated data type display underscore 4. Declare the component time underscore set along with its port list. Declare the local signals, generate the clock and apply the reset. In the process, HSGen generate the half-second pulses. The pulse is synchronized to every third clock period with multiple wait statements in a loop. Instantiate the time set component, initialize the inputs and synchronize it to the negative edge of the clock. We shall verify the time adjustment functionality by driving show underscore t high for one clock cycle. This will load the value of time underscore data, which is 55 minutes, into the BCD counters. Then wait for 7 half seconds using a for loop to observe the rollover happen on the minute digits. Next, to verify the alarm adjustment functionality, we drive the signal show underscore AI for one clock. This will load the BCD counter with alarm underscore data value, which is 19 now. We then increment the hour by driving high on inc hour. We wait for 7 half seconds using a for loop to observe the rollover happen on the hour component of the time.
Let us run the simulation by executing the extern command. Select the top file, send to waveform window, press the play icon, adjust the time scale and the zoom option. The signals alarm underscore data, time underscore data and set underscore data are all array of arrays and hence their values will not be displayed in the waveform window. Let us expand this one level down in order to observe the digits individually. We see that when the reset is active, the output are all zeros. At 30 nanoseconds, the value of show underscore t is high and the value of time underscore data is 55. Hence, set underscore data takes the value 55. Let us observe the value of set underscore data increment from 55 to 56 to 57 to 58 to 59 and then it rolls over to zeros. This illustrates the minute count rollover for minutes BCD counter. Let us verify the alarm time increment feature. At 450 nanoseconds, we drive show underscore AI and the value of alarm underscore data to be 1900. Hence, the output set underscore data takes the value 1900. We then apply increment hour high for 7 half second pulses and we see the output set underscore data increment to 20, 21, 22, 23 and it rolls over to 00. This illustrates the hour count rollover for hours BCD counter. Let us synthesize this design.
Set the design file to time underscore set. Read the file p underscore alarm underscore types.vht and bcd2 underscore count.vht along with the design file. Execute the Janus shell script. Select the top file and send to schematic. We can see the synthesized design. Here, the synthesized design is in terms of AND gate, OR gate, and other primitive gates, and not in terms of the BCD component because of the optimization by the synthesis tool. To view the schematic in terms of the BCD counter components, add the suspend command after the elaborate to disable the optimization. Let us run the script by executing the genus command. We see that the process suspend after executing the suspend command. Let us view the schematic executing GUI underscore show command. Select the top file and send to schematic. We see the synthesized circuit is now in terms of the BCD component and the MUX component. Let us zoom the schematic and view the details. We see that there is a MUX for each bit of alarm underscore data and time underscore data. The output of this MUX is fed into the BCD2 underscore component. The output of the BCD2 component is set underscore data. There are two instantiations of BCD2 underscore component, one for the minute and other for the hour. We see that show underscore A and show underscore T are ORed, and the output of the OR gate is fed into the load enable of the BCD2 components. Also, we see that the AND of half second and increment min is given as input to the minute instantiation of the BCD2 component. Similarly, the AND of increment hour and half second pulse is given as the count enable for the hour instantiation of the BCD2 component. This completes this lab.